where we have to find the shear and moment diagrams for this beam. So the first thing we need to do in this case is calculate the equations. So find the equations for the shear force and moment diagrams, and then figure out what that looks like at each different point. Before we did it using the point of section, but I'm straight away going to start using equations. Before I do use the equations, I do, however, have to find the support reaction. So the first thing I'm going to do here is I'm going to find the support reactions. And in this question, I have a support at A, which is a pin, and I have a support at B, which is a roller. Roller allows moment in X direction only, therefore it causes or it develops a reaction in the Y direction. Pin restricts movement in both X and Y, therefore there's going to be a reaction in the X and Y directions both. So that's the idea. So I need to find the support reactions, which are going to be AX, AY, and BY. And for that, we're going to utilize the equations of equilibrium. The loading that we have over here is a uniform loading of 40 kilonewtons per meter. What I'm going to do is I'm going to just convert this into a point load, which is going to be very easy for us to do. So there's A here. Let's say here's B with a roller. And then here's just C. At C, we have a 20 kilonewton load acting downwards. When I calculate the area of this, it's going to be 40 times 8, which is 320. So that's going to be the loading at the point load. And because it's a symmetrical rectangle, it's going to act, exactly in the middle of 8, which is going to be 4 meters away from A. There is going to be a loading of 320 kilonewtons acting exactly 4 meters away from A. Again, A has both AY and AX reactions. B only has BY. So we have 3 unknowns, and this is our equation. The best way to go about this, to find the reactions, is first take a moment about A. But before we even take the moments, we can clearly see that AX is going to be 0 because there's no other force in the X direction. There's no other loading in X direction, so it must be 0. And then we can take moment about A, counterclockwise being positive. You do all of that and you will get 320, which is 4 meters away, clockwise, so negative. BY, counterclockwise, so positive, acting 8 meters away. C is actually clockwise, so 20. And using that, I think the B we figured out is just going to be 187.5 kilonewtons. And then we can just use the sum of forces in the Y direction is all 0, considering upwards to be the positive direction. We get that AY is equal to 152.5 kilonewtons. Okay. Now that we have this, we can start developing our, first of all, shear equations. So I'm going to use this to form shear equations first. So shear equation goes like this. It's going to be like a linear equation, usually in the form of y equals b plus mx. The sign here, positive or negative, depends on the direction of loading. When loading is downwards, this is supposed to be a negative sign. So the slope is this 40 kilonewtons per meter. That is going to be the slope, which is going to be represented by the letter M. And B is the initial force, which is going to be whatever the force is at the starting point, which in our case is A. So let's consider A to be our starting point. So this equation Vx is V naught, and then minus whatever your loading is, which is 40 kilonewtons per meter X. V naught is the reaction at A, which is 152.5, and it's acting up. which means I'm going to replace this with 152.5. This is the equation for the shear force. This is only valid though from A to B, because that's where the loading ends, right? So the loading is ending at this point B. Therefore, it's only valid from A to B. So let's figure out the loading. So V naught, which basically means at the starting point, it's 152.5 kilonewtons. We can figure out what happens when V goes to 8. So, which is basically me trying to find out what is happening at B, which is 8 meters away. So right here, what's happening at B. So for that, all you have to do is just plug your X as 8 here. You do the math, and I think we got negative 167.5 kilonewtons. If I am to draw the graph right here, so at 0, we had 152.5. And then going from 0 to 8, we went all the way here to negative 166.5. So that is kind of what happened between 0 and 8, right? Now, what happened at 8? So at 8, so let's say when we calculated, it's like right before the point B, which is like before we account for this BY reaction. So what happened at this point at X equals 8, what happens is, yes, you got this, but then BY reaction is also added. Okay, so if we account for that, then V at 8 would be this, which we got because of the loading. And then we add the BY reaction, which is 187.5. So we add 187.5 and we got the answer of 20 kilonewtons, which means right here, there's going to be a jump where it will go up and go here at 20 kilonewtons. Okay, so that's it, that we're done from A to B. Now we will think what happens between B and C, which is from 8 to 11. So now we're going to think from, so this one was from A to B. So X equals 0 to X equals, what is it, 8. Here from B to C, which is from X equals 8 to X equals 11. Here, if I look at this diagram, there's absolutely no loading between B and C. So because there's no loading, there's no slope. So if we look at this equation here, we know that this part of the equation exists because of loading, where M is however much loading is being applied per meter. And so from B to C, because there's no loading, the Vx formula is going to be V naught, which is going to be the starting point force at 8. Okay, so I can also call it V8 actually. And then the mx is just because there's no loading, so it's 0x because there's no loading. So the equation is Vx equals V8, which we know is 20. We just figured that out. So Vx equals 20. This is what the equation is going to be from x equals 8 to 11, which means from 8 to 11 all the way, the shear force is going to be constant 20. Okay. Now we know at 11 something else happens. We know at 11, sorry, over here. We know at 11 there is a negative 20 kilonewtons load that is being applied. So we'll see at C, which is at X equals 11, we're going to account for the negative 20 kilonewton force. Therefore, we'll start with this 20, and then we will add the negative 20 kilonewton force, which will result in the shear force going to 0. So in our diagram, we're gonna bring it back to 0. Okay, so those are the equations for the shear force, and this is how the shear diagram is gonna look like. Now, I'm gonna do the moment equations right here. Before I proceed, let me just quickly text my other student. I'm gonna be a little late to the Okay, so now we're gonna do moment equations. The good thing about moment equations is you don't have to think much because all the moment equations are just dependent on the shear equations integration. So for example, from A to B, so exactly here, from A to B, here's what a moment equation looks like. This plus the integration from 0 to x of Vx dx. So the moment at A, it's a pin. It does not restrict bending moment. And so there is no moment at A position. So at 0 position, there's no moment here. But then we have the equation for Vx, which is this one. So I'm gonna just write this exact same equation over here. It's going to be 152.5 minus 40 x dx. And if I do integrate it, I will get mx is equal to 152.5 x minus 20 x squared. And it goes from 0 to x. So you could put any values of x here and figure out what's going to happen to the moment anywhere between from 0 to 8 or A to B. Now, one thing to note is your moment will become max exactly where your shear force goes to 0. Okay, so you'll get your max moment when shear goes to 0. So bending moment goes to max when shear goes to 0. So if you want to figure out where your max moment is, all you have to do is just figure out where your shear goes to 0. So I'm going to do that on the side here. Where does the Vx goes to 0 between A and B? So for that, all we have to do is just, again, take this equation, put it equal to 0, and figure out for what value of x are you going to have a shear moment of 0, and it's going to be this value of x. So we'll put that in here to find max moment. So if you do that and you put the value 3.8125, 3.8125 squared, turns out that our max moment is 290.7 kilonewton, and that happens at x equals 3.8125. So if we were to start actually graphing the moment graph here, it'll start at 0, and then at 3.8125, it will reach a maximum of, let's say, 290.7. It's kind of like this. And then we can see what happens at x equals 8, because, that's the next big point that we have to cover. Ideally, we should draw them right, like underneath each other so we can like keep track of what's happening, kind of like this. But for now, let's just do it here. So the next big point is what happens to the moment at m equals 8. So again, in this very same equation, I'm going to just input x as 8. See what my bending moment is. And I think it is -60 here. So from here goes all the way to, let's say here, -60. And then we have to see what happens from here till 11. So this is basically from 8, sorry, not A, but B actually. From B to C, which is x equals 8 to x equals 11. Again, we will use the exact same, actually, it doesn't have to be from 0 now, it will be from 8 to 11, dx, dx. Or you could, yeah. So the moment now that we will start with is -60. And then Vx from B to C is this equation, just Vx is just 20. So I'm just going to do integration of 20 dx, which is going to be -60 plus 20x, that is mx. So if you want to find out what happens at 11, now 8 to 11, if you could do 8 to 11, or it's good if we do from 0 to 3, because 8 to 11 is a difference of 3 units. Because we're starting exactly at -60, so kind of like the new graph begins at x equals 8, you can imagine this is x equals 0, this is x equals 3. So we put x as 3 to see what happens at, overall the 11. This is going to be 0, so over here, you'll make a linear line which goes to 0, and that is it. I just stopped the recording.